In this module we will discuss electromagnetism and its applications and theories. In 1806 Ørsted became a professor at the University of Copenhagen, where his first physical researches dealt with electric currents and acoustics. During an evening lecture in April 1820, Ørsted discovered that a magnetic needle aligns itself perpendicularly to a current-carrying wire, definite experimental evidence of the relationship between electricity and magnetism. The behavior of the compass will align with respect to the direction of the current. Here we have a demonstration of the experiment. As the wire is connected together allowing the flow of current, we see the compass deflecting. This is because the flow of current produces a magnetic field which the compass reacts to since it has a magnetic material attached to it. Electromagnetism is one of the fundamental forces that governs the universe. It is responsible for flow of current in wires and magnetic interaction of materials that have magnetic qualities. Its range of effect is infinite and it can be demonstrated by the electromagnetic radiation emitted by far-away objects like distant stars. Here you can see the other fundamental forces, which are the strong force, weak force, and gravitational force. The strongest force among them is the strong force that binds the nucleus, and the weakest is the gravitational forces. The electromagnetic force is 1/37. A weak force is related to radioactive decay, where a particle emits release of particles. Here we have different particles that are associated with these forces. In this module we will focus only on the electromagnetic forces, but you can look up the other forces. Greek philosopher Thales of Miletus wrote about the nature of certain stone amber that is able to attract light materials such as feather when it is rubbed, demonstrating the behavior of static electricity. A special type of stones are called magnetite that is able to attract iron fillings like this lodestone, which is a naturally occurring material. You can also observe static electricity when you brush your hair, that when the condition is sufficient enough, such as dryness of the hair, will result in hair raising due to static electricity. When combing hair which is initially neutral, having equal amounts of positive and negative charge, it becomes imbalanced. This is because the negative charged electrons leave the hair and transfer to the plastic comb. The comb is initially neutral also, but due to rubbing the positive and negative charge are reorganized. Since there is a transfer of the negative electrons, the comb becomes more negative and the hair becomes positive. Since the hair is more positive, the individual strands repel each other, making it appear that they are standing up. Shown in the figure, a woman has hair with an initial amount of net charge of 0, meaning the positive and negative charge are 0. The comb has also an initial amount of net charge of 0. After rubbing, the total charge of the hair after most of its electrons leave is now a positive net charge, and the hair which gains more electrons becomes a negative net charge. Here we have a simulation regarding charges. When you have a positive charge, the vector field of arrows is directed outwards, and for negative charges it is directed inwards. Here we have a simulation regarding charges. When you have a positive charge, the vector field of arrows is directed outwards, and for negative charges it is directed inwards. When two charges are placed near each other, we can have two different effects. For opposite charges, the vector field appears to connect from the positive going to the negative. When they are the same type, the vector field A appears to be deflecting. The law of electric charges is simply stated as unlike charges attract one another and like charges repel each other, as shown here. Coulomb's law shows the relationship between charges. The force of attraction or repulsion between charged objects is directly proportional to the product of their magnitude of charge and inversely proportional to the square of the distance between them, as shown here by the equation. The magnitude of charge of the electron or proton is a natural unit of charge, is given by the symbol e to the power of negative. Here we compare Coulomb's law and gravitational force. They appear to be identical and similar in terms of interaction. We replace the masses in the gravitational formulation with the mass of charges. Instead of a gravitational constant, Coulomb's law has the proportionality constant. Conservation of charge simply states that the transfer of charge does not create new charge or destroy a charge, it simply migrates it, and the total charge of the system remains constant, giving a total net charge of 0. Here we have a strand of hair and a comb that are initially neutral, which means they have equal number of electrons and protons. Both become charged after they are rubbed together, creating a positively charged hair and a negatively charged comb. Since charge is conserved, then the sum of these protons and electrons is 0. Insulators and conductors are used in electronics to control the flow of electricity. Wires are composed of a conducting core which is metallic in nature and an insulator coating that is typically rubber. The other material is a semiconductor which exhibits a conducting and insulating behavior, and it is the heart of integrated circuit devices. The reason for the difference of behavior is due to their energy band gap differences. If we consider a single atom, there are, according to the Bohr model of atoms, sharply distinct energy levels, which may be occupied by electrons. If there are multiple atoms side by side, they are interdependent, the discrete energy levels are fanned out. In a silicon crystal, there are approximately 10 to the power of 23 atoms per cubic centimeter, so that the individual energy levels are no longer distinguishable from each other and thus form broad energy ranges. A useful way to visualize the difference between conductors, insulators, and semiconductors is to plot the available energies for electrons in the materials. Instead of having discrete energies as in the case of free atoms, the available energy states form bands. Crucial to the conduction process is whether or not there are electrons in the conduction band. In insulators, the electrons in the valence band are separated by a large gap from the conduction band. In conductors like metals, the valence band overlaps the conduction band, and in semiconductors there is a small enough gap between the valence and conduction bands that thermal or other excitation can bridge the gap. With such a small gap, the presence of a small percentage of a doping material can increase conductivity dramatically. Neutral objects can be charged by creating an imbalance of the charges. One way of charging is by conduction, where it is done through physical contact. Here we have a neutral sphere having equal amounts of positive and negative charge. A negatively charged rod is brought close to the sphere by physical contact. The charges that are present in the rod migrates rapidly towards the sphere and becomes a net negatively charged sphere. Another method of charging is by induction, where it is done through a non-physical contact. We have two neutral spheres that are in contact and a net negatively charged sphere is brought close to them. The negatively charged object is brought close but no physical contact, and the charges inside the spheres are displaced due to the attraction of the positive charges. One sphere will become positively charged and the other is negatively charged, and when they are separated both spheres are charged. One sphere is net positively charged and the other is net negatively charged. We know that when two charges are present they exert a force given by Coulomb's law. The force is of equal magnitude and depends on the type of charge if they are an attractive or repulsive type of interaction. For a case where there are more than two charged objects, we express the force relationship as a sum of the individual interaction. Sample problem. 2-point charges, Q1 equals 25 nanocoulomb and Q2 equals negative 75 nanocoulomb, are separated by a distance r equals 3 cm. Find the magnitude and direction of the electric force, letter A that Q1 exerts on Q2 and letter B that Q2 exerts on Q1. Let us look how the force orientation is exerted by Q1A on Q2 and by Q2 on Q1. Charges of opposite signs are attracted towards each other. We expect that the forces will be oriented towards each other. For the force exerted by Q1 on Q2, we examine its effect on the charge and it is oriented towards the Q1. For the force exerted by Q2 on Q1, we examine its effect on the charge and it is oriented towards the Q2. We see that the forces here are of equal proportion but in opposite directions, such that we write their relationship in equation A. To solve for the magnitude we use equation 2. For letter A and B we have the magnitude of the force being exerted is about 0.019 newtons. Sample problem. Two equal charges Q1 equals Q2 equals 2 microcoulomb are located at x equals 0, y equals 0.3 meters and x equals 0, y equals negative 0.3 meters, respectively. What is the magnitude and direction of the total electric force that these charges exert on a third charge Q equals negative 4 microcoulomb located at x equals 0.4 meters and y equals 0? We examine the forces that are being exerted by Q1 and Q2 charges. Since they are the identical, the magnitude of their forces exerted will be the same but oriented indifferently. From the figure we see that the components along x are oriented the same, so the forces along x-axis will add up. However, the components of forces along the y-axis are oriented in the opposite direction, so they cancel each other out. So we sum of forces along x and y as shown here in equation A and B. So the net force exerted on the charge Q is given by C, and simplifying it we have equation D. Applying the equation of electric force 2 and substituting this back we have equation E. Let us determine some of the quantities here. The cosine function and distance are the angle theta is determined by calculating the cosine function by using the geometry of the angle theta. So the function of cosine theta is given by equation F. The distance r is obtained by using Pythagorean theorem. We have equation G. Substituting this back to equation F we have an expression for the cosine function h. Substituting the equations G and H back to equation E we have the resultant force due to the charges to be about 0.46 newtons directed in the x direction as indicated by the unit vector I hat. Sample problem. Consider 3-point charges located at the corners of a triangle as shown in the figure, where Q1 equals Q3 equals 5 microcoulomb, Q2 equals -2 microcoulomb and A equals 0.1 meters. Find the electric force on Q3. Refer to the figure. At the location of AQ3, the total electric force is a vector sum of the individual fields produced by Q1 and Q2. Note that the force exerted by Q1 on Q3 lies on the x and y plane, so we consider its components. So we write an expression of its component as a function of theta shown in equation A and B. So we write the sum of force along x and y as in equation C and D. Let us consider solving the angle theta. By geometry we see that the sine and cosine of this angle can be expressed as these functions here. Consider the adjacent and hypotenuse parts. For the cosine function we have equation E and sine function as shown in equation F. We will substitute them later. Recall the expression of force by two charges we have equation 4. So we have for the forces along x, which is the sum of the components from force 1 and force 2. We get that the sum of forces is a negative value that suggests that it favors going in the direction along the x-axis as indicated by equation G. Considering the forces along the y-axis we have from equation D. We get that the net force along y is pointed upwards since it is positive as shown in equation H. Here we have the resultant force, which is expressed by its components along the x and y axis from equations G and H as shown by equation I. Based on the signs of its components, the resultant is oriented on the second quadrant as shown by the figure. We can also solve for the magnitude and direction of this resultant force. For the resultant we use the Pythagorean theorem as shown by equation J, which is about 8.6 newtons. For the direction, we take the negative x-axis as the reference, and using the tangent function where we take its absolute value we get that the resultant force is 6.9 degrees with respect to the negative x-axis. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and a class section. A thank you for listening and see you next module.